We're going to do the harder buffered solution now. But the Henderson-Hasselbalch equation goes like this, where they deals with a pH of a buffered solution is equal to the pKa. Remember, in a buffered solution, you're going to have a conjugate acid-base pair plus log of base 10. And you can either go with the ratio of the molar concentration of base to acid or the moles to base to acid. Same diff. Just say or moles of base to moles of acid. Okay, so yeah, a buffered solution has a conjugate acid-base pair running around in there. And we talked about how you can just sprinkle, well, I think the ones we did was like you had a solution of that had one of the species and then you added the other species. Well, today I'm going to talk about this other one where you have a weak acid or weak base minding its own business, and you're going to add some strong acid or strong base to convert part of it to its conjugate. Okay, so I think I only have one example, but it works both ways. So here's what this one looks like. So let's see. Looks like I have a volume down here, 150 milliliters. And notice I've got 0.123 molar NH3. So hopefully you've been finding your way around. So you're like, does this seem like it would be a proton donor? How many people think this seems like it would be a proton donor? Donor. Proton acceptor. Okay, why is it an acceptor? Because you can kind of picture the NH4 plus. Yeah. So yep, this is an acceptor. So actually this is a weak base. Okay. Notice the problem says that what we're going to do, and it feels kind of strange, we are going to drip in HCl. Specifically, I have the molar concentration of 0.0883 molar HCl. So this is a strong acid, right? And this is what, let's finish with what else it says. So what volume, so question mark volume of this strong acid do we need to drip in order to get a buffered solution that has a pH of 9.50? So here's how the chemistry works. What's going to happen is every HCl I dump in here, every drop is going to go ahead and convert or react with ammonia to form ammonium chloride. It's what we call, I think on my slide it says a limited reactant. It is going to gobble. That's just the way this works. We have a weak base. Notice I've got a one-way arrow here. And a strong acid. You're going to get the conjugate acid. It's supposed to be CONG-J. Oh, drat. That's just what it does. Doop. Maybe. Okay. So looking a little bit more closely at, all right. So how do I say this? I think I'll do it on the board. So basically, as you drip this in, what you're going to get to form is NH4 plus. And that is your weak acid. Specifically, it's the conjugate weak acid, conjugate acid of your weak base. And that makes your buffered solution. So you can see on the next slide, one of the things I need for my Henderson-Hasselbalch equation is I need the pKa. And this is the one where I complained the other day that I'm like, why do we keep doing this? And I told you this was coming. You're not going to find a Ka for NH4 plus. You will find a Kb for NH3. So this is where we kind of have to reverse engineer it. We know that has the relationship Ka times Kb is equal to Kw. We can rearrange that, and get Ka is equal to Kw over Kb. Assuming that we're dealing with 25 degrees Celsius, then you know the Kw is 1.0 times 10 to the negative 14th, and you will be given the Kb of NH3. So we're going to have to put that. This is how we get to the Ka of NH4 plus. So 2 sig figs, then our Ka is 5.6 times 10 to the negative 10. So I think in my slides I've been doing this. Let's do a quick check to see if this conjugate acid-base pair, if it would be a good one for target 9.50. So we can just do a quick, get the pKa, which would be negative log of the Ka, so negative log base 10 of 5.6 times 10 to the negative 10th, and you're looking at 9.26. So this actually does 2 things. It kind of checks to make sure our conjugate acid-base pair are a good one for this target pH, and you figure that's my now I have this now, so I'm ready to rock and roll with that. That is 9.26 for this problem. Okay. Oops, go backwards. So this one gets a little more interesting because we have to kind of massage this volume, understanding the chemistry that I just showed you, where HCl reacts with NH3 to form NH4, NH4Cl. So when we look at the Henderson-Hasselbalch equation, we know this, this is our 9.50, and we actually know the molar concentration of our base in a way. So our base is going to be NH3. I will warn you though, and one of my slides says that your NH3 is a moving target because you're adding HCl. Okay, so I'll show you how we handle that. And your acid is going to be your NH4 plus. So that's kind of what we have going on. I'll tell you the best way to do this is to go ahead and rearrange your Henderson-Hasselbalch equation. We did this the other day. Remember that we can take 10 raised to the power and kind of isolate the ratio of the molar concentration of the base to the acid. And we get this form of it. So we did this the other day. So the ratio of the moles of base to the moles of acid will be equal to 10 raised to the pH minus the pKa. And we have the target pH and we have the pKa, so that's pretty easy. Okay, so how are we going to handle this moles or ratio of base to acid? Again, NH3 to NH4 plus, knowing that as we drip in, NH3 goes down and NH4 plus goes up. Okay. So now this is a warning that here in the Henderson-Hasselbalch equation, notice what I don't have basically is anything necessarily to do with the HCl. The HCl is just going to help us. It's going to be all gobbled up. There won't be any HCl in the solution at equilibrium. It's the source of creating the NH4 plus. And then this is the moving target I talked about. Remember that, or you have to envision that this molar concentration is going to go down. Okay, it's not going to be 0.123 molar after we add HCl to it. So some of that NH3 is going to will go to form our NH4 plus. Okay. And we're going to assume that the volume that we add from the HCl doesn't change our 150. Seems reasonable. Okay. All right. So like I said, in this sort of problem, all of your strong acid is going to be totally used up. So we need to find out the number of moles that will be moles of NH3 that will be converted. Okay. Then the moles of NH3 remaining, that's going to go in our Henderson-Hasselbalch equation. And the moles of NH4 plus, that's going to go in our Henderson-Hasselbalch equation. And I think this is the first time I've introduced, did I do millimoles before? I don't think I did. Milliliters are awesome, but you have this whole, if you want to use molarity and you have milliliters, you have to go from milliliters to liters, and then you can use molarity. Well, here's this cool idea. If we keep, how do I say this? We can keep the, I'm kind of talking about the pink thing down here. Molarity, we know, is moles of solute per liter of solution. Molarity is also millimoles of solute per milliliters of solution. So if we introduce, instead of moles, this idea of millimoles, then we don't have to go back and forth between from milliliters to liters. So I'm gonna introduce that now. So the title of this slide is millimoles of NH3 present in the beginning. So we can get that from this information. We have the 150 milliliters of solution. We can introduce the molarity. Now in this case, I'm gonna go with 0.123 millimoles of NH3 over 1 milliliter of solution. That gives us 18.5 millimoles. Aren't they adorable? Millimoles are just gorgeous. Okay, so I think I'll do it this way. A few slides ago, we said that this initial conversion of NH3 to NH4 looks like this. So all of this will be consumed. NH4 plus, that's what we're curious about. We don't care about the chloride ion. So I'm going to put this here. Not an HCl. I'm going to put it right here. 18.5 millimoles under my NH3. All right. So if I'm going to introduce a variable x, and if we let x be equal to the millimoles of, I'll put initial here. If we let, this isn't really an ice table, but it kind of a little remotely reminds me of one. So if we let x be equal to the HCl that's added, so notice then that the stoichiometry, we got that boring stoichiometry 1 to 1 to 1 across the board, then that means that this actually, I maybe call this a minus x, I don't know. This is however x much we put in here, that's what's going to react with our NH3, and then actually that's what's going to be formed over here. I don't know if I'm going to put a plus x, I don't know. Maybe that works. But this is all going to be gone. There's none of this left. So when we're done, when we've added the HCl that we want to add to get to our pH 9.50, again, all of that strong acid's going to be gone. How much of the NH3 are we going to have left? Well, 18.5 minus x. How much of the NH4 we're going to have? X. So if the stoichiometry was not 1 to 1 to 1, these would not just be simple x's. Okay? All right. Well, now we've got something we can deal with, because what I'm after is this ratio right here, and actually I've got some numbers here. So here in a minute you're going to see this one go in the top and this one go in the bottom. Okay? So we go back to our Henderson-Hasselbalch equation where we have the ratio of the moles of base to the moles of acid. We plug in what we've been working on here, setting up what would those moles look like relative to an X. And remember, X is the amount, is going to be the millimoles of HCl I add. So this actually, if you're like me, I'm not a real mathy sort of person, this will not, you will not have to use the quadratic equation. We can go ahead and I would kind of clean this up by taking 10 raised to that power first. I write that number down, then I kind of cross multiply that number times x is equal to 18.5 minus x. gather your x terms and you're set. You actually can then solve easily for x, and you'll get a value of x is equal to 6.75 millimoles. And what does that mean? That is actually the millimoles of HCl you need to add in order to get this whole thing to work. It's just a beautiful sort of kind of balance here. All right. So we need to backtrack from those millimoles and get to volume, of HCl, given that molarity. So if our target is 6.75 millimoles, we're going to use the molarity here. Stick with the whole idea of millimoles, so that would be 1 milliliter of solution over 0.0883 millimoles of HCl. Units of millimoles of HCl cancel, we're left with units of milliliters, which is perfect. 3 sig figs, and you're looking at 76.5 milliliters of that strong acid is what you would need to go ahead and dump into that weak base to get just the right amount of conjugate acid formed. It's magic. So in this case, we took a weak base, added a strong acid, all the strong acid was used up, and created the conjugate acid. We could have taken a weak acid and added a strong base to create its conjugate base. And the same thing. Okay, so, and remember there's just a few more that weren't listed that will be due as part of this. Okay? All right, so tomorrow's lab is one of those where you're gonna have to, you'll be doing it, and we haven't really covered it entirely in lecture yet. So it's just the way it goes. So for pre-lab, I'll try to kind of fill you in on the blanks, any blanks you might need to know while you're doing your lab. But tomorrow's lab, you guys are doing a titration, and you're going to be tracking pH as you do the titration. You guys have done with the burette and all that, so. What's that? One of the things that's a challenge is to understand the chemistry that's going on, and you need to recognize your strong acids. There's 6 strong acids you need to memorize, and if something's a strong base, and then everything else is weak, and the chemistry will be different. I'm going to kind of walk you through the different possibilities of strong and weak and all that. So we could have a strong acid and a strong base. So that'd be SA plus SB. We could have a weak acid and a strong base. We could have a strong acid and a weak base. Last but not least, they could both be weak. Weak acid and weak base. So these are the sort of titration scenarios for acid-base reaction. I guess it wouldn't have to be a titration, but acid-base reactions. In all of those acid-base reactions, we should be able to look on both sides of the reaction arrow and then identify, we've talked a little bit about this, 2 pairs of conjugate acid-base pairs. And as far as conjugate acid-base pairs, they differ by a proton. I think you guys have been kind of dealing with that here and there. So in this list, these are, if I could circle any pair, they would differ by a proton. Acids on the left and bases on the right. So taking them one by one, we could look at this one. HCl is one of the 6 strong acids you need to memorize. Sodium hydroxide, it's a strong base. And the products would be NaCl and H2O. We could break up what sort of species we have going on there. The AQ means it's dissolved in water, so that's fair game. We identify on both sides that HCl would be the proton donor, its conjugate base would be the chlorine ion. As far as the other acid-base pair, the hydroxide ion would be the base. Proton acceptor on the product side, it would be H2O, would be its conjugate acid. I know it seems weird, but that is true. The net ionic equation, we can remove spectator ions. Looks like removing the sodium and the chloride. And you get this simply with a strong acid and a strong base. Example of a weak acid and a strong base. This actually, excuse me, is what you guys will be doing tomorrow, I think, if I'm remembering this right. This is acetic acid, CH3COOH. And this is a weak acid and strong base. So if we kind of break it apart, see what we got going on, you can see our acid on the reactant side would be the acetic acid. On the product side, it's the acetate ion, that's conjugate base. On the reactant side, the base is the hydroxide ion, and its conjugate acid would be water. Net ionic equation, remove spectator ions. Looks like we can just remove the sodium. There's a net ionic equation. All right, NH3, weak base. HCl, strong acid. We can identify the two conjugate acid-base pairs on both sides, differ by proton. Net ionic equation, we can remove the chloride ion. And then last but not least, I take a couple that we looked at earlier, acetic acid and ammonia. And so this is a weak acid and a weak base. Break it up into its ions. Show the conjugate acid-base pair on either side. Remove, there are no spectator ions to be removed. Okay, so chemistry going on behind the scenes. In a titration, I know this says acid-base reaction, but I think of it in a I guess this would be in any acid-base reaction, we can think of three things going on. Actually, the overall reaction is the product or the summation of three things going on. One is the acid kicking off a proton, the ionization of the acid. The other is the base picking up a proton, the hydrolysis of the base. And Ka is what we summarize kind of step one. Kb is step two. And then the last one is the protonation of the hydroxide ion. So the H plus and the OH minus come together, and actually we would call that forming water, which actually forming water is the reverse or the inverse of water breaking down. So forming water is the inverse of Kw. So if these are the three things happening behind the scenes, then we can actually bring them all together by multiplying them together. So if we take Ka times Kb divided by Kw, that actually is the K of your overall acid-base reaction. And this really kind of threw me off, and I did not figure it out, but, this says, I'll finish this thought and then I'll come back to my other thought. So this says that if Ka or Kb are relatively large, then your K of your reaction is relatively large. And what do we know about that? It favors the product side. We've learned that about equilibrium. What I started to say is Ka times Kb for conjugate acid-base pair is Kw. So I'm like, this is Kw over Kw. I don't know. I didn't track it down. I'm just like, anyway. All right, so this is just kind of thinking through things. Now, the word equal molar is underlined. So if we have the equal number of moles of a strong acid and equal number of moles of a strong base, they are going to, what we say, annihilate each other. So when the dust finally settles, you're not going to have anything left. That's to say that you're not going to have any H pluses, you're not going to have any OH minuses, which makes your solution neutral. Okay? No extra ones anyway, autoionization, but That's not the case if you, and we, let's see, did we do that? No. If you are having equal molar quantities of a weak acid and a strong base, what's going to happen is your strong base is going to convert your weak acid to its conjugate weak base. Okay, so actually you're going to end up with a basic solution, so the pH will be higher than 7. What will be the pH? The driving force of this solution will be the formation of, like I said, the conjugate base of the weak acid. It's not basic because of your strong base, because it's all used up. It's basic because you have formed that conjugate weak base. Again, equal molar quantities. What if, and we just did this one over here. What if you have a strong acid added to a weak base in equal moles? Well, all of your weak base is actually going to be converted to its conjugate acid. So you're looking at an acidic solution, but what's driving the acidity of that solution is not the strong acid, because that's been entirely used up. What's driving it actually is the presence of that conjugate weak acid. Then the last scenario I had was a weak acid and a weak base, equal molar quantities. As you might imagine, it just kind of depends on the nature of the weak acid and the weak base. It could be neutral, could be acidic, it could be basic. I can't tell for sure, like I could tell those other 3 scenarios. So we're not going to worry really about the 4th scenario, because it's a kind of what if, but we are going to worry ourselves about the especially right now, actually the example I have with the first 3. Okay, these are going to be like deja vu. You're like, we already did that in Chem 1, and you're right. So the titrant is the thing you put in the burette. The analyte is the thing that you're dripping into. You're dripping it into it. The equivalence point, and we did phenolphthalein indicator in Chem 1. The equivalence point was when you got that pink color that just stayed, okay? Equivalence point, equivalence volume. Now there's a slight difference between, all right. The salt actually is on the product side. Acid-base reaction will always give you a salt. I'll kind of show you what that looks like. So when you're titrating, there's 3 reagents that have different chemistry going on, and you have to, I have a slide saying, can you identify where that equivalence point is? The equivalence point is where you have dripped in the same number of moles of titrant as you have moles of analyte, or I should say they are stoichiometrically consumed, okay? That's the equivalence point. So there's a different chemistry going on before the equivalence point, at the equivalence point, and after the equivalence point. So like I said, you're going to need to be able to kind of find where that equivalence point is. That's a Chem 1 thing. So I'm actually going to take the first of 4 types of acid-base reactions, the strong acid with the strong base, and we'll kind of think through. We'll actually do some number crunching. Okay. Strong base. The NaCl is the salt I talked about a minute ago, and of course water. So in this case, let's draw a picture. We are going to, our analyte, oftentimes, and that's going to be the case tomorrow, the analyte's acid. It wouldn't always have to be, but we have 25.00 milliliters of 0.100 molar HCl. And we are going to drip in, here's my burette, my little stopcock thing. We're going to drip in 0.100 molar NaOH. There we go. So we're supposed to come up with some problems. Let's see, I don't want to say this. But do you guys buy this? I think you probably do. That the balanced equation if we start out with 25.00 milliliters, 0.100 molar. And then this was also the molar concentration of our titrant is 0.100 molar. Do you guys buy this? That actually the equivalence point, this is going to be a volume of 25.00 milliliters. Okay, just because the stoichiometry and all that. So that dotted thing, that actually is our equivalence volume. Cool. So we're going to look at we're going to knock out the pH when we've only done 20 milliliters. And then we're going to knock out the pH when we've done 25 milliliters. And then we're going to knock out the pH when we've done 30 milliliters of titrant. Okay, so that's before the equivalence point, at the equivalence point, and beyond the equivalence point. All right, cool. So at 20 milliliters, then, you figure all of the NaOH that you've added has been consumed, and you have extra HCl. So that's what's going to be actually driving the pH, is your extra HCl that hasn't been used up. Okay. So before the equivalence point, like I said, you just have extra HCl. So we need to, I call it kind of counting beans. So I'm going to change this to 20. Basically, at that point, you're gonna see me go ahead and come up with the millimoles of this and the millimoles of this and do some math and see how much of this I have left. The catch is, and you're gonna see me do it at the end there, once we get the millimoles of HCl you have left, we have to divide it by, check this out, 45 milliliters. That's one of the catches. Why? Because that's how much we have in our little beaker now. Okay, so here we go. Millimoles HCl present, 25.00 milliliters times 0.100 millimoles HCl per milliliter solution. Just need to move the decimal place over once, don't we? So that gives us 2.50 millimoles of HCl that we had when we started. So at that point in the titration, how many millimoles of NaOH did we add? So we can use the volume and molarity. So we added 20.0 milliliters of NaOH. Its molarity was also 0.1, so we have 0.100 millimoles of NaOH per milliliter solution. So that means that we have dripped in 2.00 millimoles of NaOH. All right. Then we need to say how many millimoles of HCl reacted. And again, we have that boring stoichiometry, but I'll go ahead and introduce the stoichiometric ratio. 1 millimole of HCl over 1 millimole of NaOH. Okay, times our 2.00 millimoles of NaOH we added. So not so surprising then, that means that we have used up 2.00 millimoles of our original HCl. So you know what I'm going to do next. I'm going to subtract that amount of from what we started with. It's like counting beans. We can get the HCl that was remaining by difference. So previous slide we had 2.50. Now this is the HCl. minus 2.00 millimoles of HCl. So we have a half a millimole of HCl. And this is where I said a really common error would be to say, what do I do with that next? So on the next slide, you're going to see me take that millimoles of HCl divided by the total volume at that time in the titration. So we can knock out the molar concentration of the HCl is going to be 0.50 millimoles HCl divided by 45 milliliters of solution. 2 sig figs, and you're looking at 0.011 molar HCl. And we're supposed to get pH, and so recognize that this is a monoprotic strong acid. So that means that my hydrogen ion concentration, molar concentration, is also 0.011. And we know, you know how to get pH from the hydrogen, the molar concentration of hydrogen ion. We're going to take the negative log of that number. So log of 0.011 times negative 1, 2 sig figs shown after the decimal. So you're looking at a pH of 1.95 at that point in the titration. Seems reasonable. Definitely acidic. You should worry if you get a number like 10 or something. Like, oh, nope, that wasn't right. Okay. So there were 3 points of the titration we were going to do. This is the first of 3 points. The second point is really easy. So at the equivalence point, which I think you guys were all fine with me putting 25 milliliters up here, that's the equivalence point. Actually, at the equivalence point, you have used up all of your reactants and product. You have used up both reactants. And so what's formed over here, there's nothing over here to make the solution anything other than neutral. So you're going to have a neutral solution. And this will always be the case at the equivalence point of a strong acid and strong base. All right, so let's do the last one. Last one we said we're at 30. We'll change this 20 to a 30 now. Because all that means is if I do this, I can remember my last step is going to be to divide now by, what, 55 milliliters, right? So what you're going to see is a similar thing where we're going to knock out the millimoles. We already know the millimoles of HCl we started with, and we need to know how many millimoles of NaOH we have. Of course, there'll be more millimoles of NaOH than there was HCl, so we just need to know how much is left over here. That's what's making our solution basic. All right. So it's just driven by OH minus that didn't have any HCl to react with. So at that point in the titration, we can calculate the millimoles of NaOH this way. So we had 30.0 milliliters of NaOH times use the molarity of NaOH, 0.100 millimoles of NaOH per milliliter of solution. We can move the decimal place over 1. That gives you 3.00 cute little millimoles of NaOH running around. Oops, looks like I have a typo there. Shouldn't that be 2.50? So millimoles of HCO, used, this would be 2.50. We know we started with 2.50 millimoles. The relationship between the millimoles of HCl and millimoles of NaOH is 1 to 1. So that means that when these are all used up, millimoles of HCl waiting to be titrated, that means that I have used 2.50 millimoles of NaOH. This gets sometimes with kind of an easy stoichiometry, it gets hard to think through sometimes, I think. Okay. So then that's the 2.50 is what's going to be used, and the 3.00 is what I have available. So by difference, 3.00 minus 2.500, that would give my, goodness, I just copied and pasted. This should be, sorry guys, final answer. That'll give me 0.50 millimoles of NaOH. And I'm almost done. So that's the excess millimoles of NaOH we have at that point in the titration. And all I gotta do is divide that number by my total volume, which would be 25 plus 30 or 55. Cool. Round to 2 sig figs. You're looking at a molar concentration of 0.00909 NaOH. So we need to tease out of there the hydroxide ion concentration. And here's where I say we recognize that that's a strong base. So that means the molar concentration of the hydroxide ion is also 0.00909. And we're after a pH. I can't remember how I did this. So there's a couple different options. We can go from, let's just see how I did it. Okay. Looks like I'm gonna knock out the POH first and then go to the pH. So the POH is equal to negative log hydroxide ion concentration. So you take negative log of 0.00909. Oh, looks like I should give myself 3 sig figs. I won't give myself 2 there. That's okay. Rounding it to just 2 decimal places, you're looking at a POH of 2.04. And we know how we can get to pH, knowing that the pH plus the POH is 14.00 at 25 degrees Celsius anyway. So we can get to the pH by taking 14.00 minus 2.04 POH, and you get 11.96. It's funny, I've told you guys that my mind is more pH scale than the POH scale. So I'm like, well, pH is equal to, if the pH is above 7, you're like, that's definitely basic. Okay. So, cool. Just kind of real quick, here's just a few slides to kind of talk you through what we just did. This is titration data where we are dripping in sodium hydroxide. You can see the volume added in moles of NaOH, and then the pH, corresponding pH. So we did this one. Wait, this one. Okay. And this one. So, you guys are going to get a curve tomorrow on your cute little LabQuest. And so the way titration curves look are along the x-axis we have the volume of titrant that you added, and along the y-axis we have pH. So you can kind of think of the reaction progressing from left to right. So what we just did is you figure at the beginning of the titration, the probe, the pH probe, was just basically in HCl. And then as we added the NaOH, okay, it started to become, the pH went up. Okay, this right here, they call it an inflection point. And it's where the curve kind of goes from this to this. So your inflection point, that actually is the equivalence point. And in this case, the equivalence point corresponded to a pH of 7. That won't be the case with you guys tomorrow when you're titrating a weak acid with a strong base. Your equivalence point actually, we talked about this a minute ago, your equivalence point will be actually at a higher pH, more basic. Okay. So we'll collect data tomorrow. You guys are gonna come up with a titration curve. I think this would be the best. And then we'll kind of talk more about your titration curve that you get tomorrow on Friday's lecture. Cool, cool.